Welcome to shear force diagram and bending moment diagram of overhang beam. Our team is Dr. Mahesh Kalyan Shetty, team leader, Professor Chetan Konapure, Professor Bipin Patil, Department of Civil Engineering, Walchand Institute of Technology, Solapur. Myself, Professor Chetan Konapure, so I am presenting SFD and BMD of overhang beam. So learning outcome at the end of this session, student will be able to calculate the shear force and bending moment of overhang beam. And even the students will be able to draw the shear force and bending moment diagrams for overhang beam and those according to the calculated values. Let's see the example problem. Draw shear force diagram and bending moment diagram for the single side overhang beam subjected to loading as shown below. So this is the problem with loading is shown. Determine the absolute maximum bending moment and shear forces and mark them on SFD and BMD. Also locate points of counterfracture if any. So you can see here beam. So span of a beam is 5 meter A to B and overhang is of 2 meter BD. So 10 kilonewton per meter UDL is acting, 2 kilonewton concentrated load is acting at C, 5 kilonewton concentrated load is acting at D. Now our first step always in SFD BMD problem, calculation of reactions. So first directly we will apply summation moment is equal to 0 at A, this point. So RB into 5 negative, UDL 10 into 4 into 2, 10 into 4 that is total load into 2, so that is positive. 2 into 4 the moment of 2 kilonewton concentrated force, 5 into 7 that is the moment of 5 kilonewton concentrated load, 7 is the distance. RB is creating anti-clockwise moment, that's why negative, and remaining loads are creating clockwise moment, that's why their moments are positive. And it is equated to 0, so RB is unknown, so RB is equal to 24.6 kilonewton upward. Now one unknown is determined and one is remaining. That's why we can apply summation if y is equal to 0. RA upward that we are assuming, so it is positive, plus RB is upward, that is 24.6 kilonewton. UDL 10 into 4 downward minus 2 kilonewton concentrated load plus 5 kilonewton concentrated load is equal to 0. So RA is 22.4 kilonewton upward. So calculation of reactions is over now. Now the shear force must be calculated at different points on this beam. Now sections are taken, and section 0 0 just left of the point A is section 1 1 right of point A, section 2 2 left of point C, 3 3 right of point C. Now these are the shear force calculation. Now shear force at 0 0 section, that is 0 because no force is acting. Now V11 that is shear force at 1 1 just right of the point A or reaction RA. So shear force at 1 1 is 22.4 kilonewton, that is the reaction RA, because the sign convention left upward of section is positive. So this is shear force at 1 1. Now shear force at section 2 2 here just left of this concentrated load. So RA upward that is 22.4 kilonewton minus total load of this UDL 10 into 4 kilonewton. So the shear force at 2 2 is negative 17.6 kilonewton. Now just right of that 2 kilonewton concentrated load, shear force at 3 3 section. Now already the shear force is calculated, so that we can take directly, or you can write equation also. Now minus 17.6. On left of the section, the 2 kilonewton force is downward, that's why it is negative. So total shear force at 3 section 19.5 kilonewton. Now shear force at 4 4 is 19.6 kilonewton as it is. No load is acting from section 3 to section 4 4. So that's why it is constant. Now shear force at 5,5 which is just right of the reaction RB. So the same shear force is continued from left of the RB, that is 19.6 plus RB, the magnitude of RB is 24.6 kilonewton. Now summation of this is 5 kilonewton. So shear force at 5,5 is 5 kilonewton. Now shear force at 6,6 just left of this concentrated force. So from B to free end of cantilever, no force is acting, that's why shear force is 5. Shear force 7,7 just right of the free end. So 5 kilonewton is a continued shear force minus this downward force on left of the section, that's why negative. So at free end of this overhang is shear force is 0. So this is a check also, and always at the free end shear force is 0. Now, various points according to their signs are marked. At A 22.4 kilonewton, at C negative 17.6 kilonewton, at left of C, on right of C it is 19.6 straight drop, and it is constant up to B. At B it is 19.6 and 5 kilonewton for positive, and at free end 0. So all these ordinates join, positive and negative ordinates are joined, and shear force diagram is ready. Now this much portion is having UDL A to C, that's why these points are joined by straight line, straight linear line. From C to B the shear force is constant, that's why horizontal line is shown. From B to D the shear force is also remaining constant, that's why it is also constantly it is shown. Now the diagram shows the variation of shear force in earlier slide. Now maximum bending moment will occur at the section where shear force is 0. So shear force is 0 according to this diagram is in between A to C. So here it is 0. But what is that distance of this point 0 shear force from any of the either of the point that we can determine? So SFD shows that the section having 0 shear force is available in the portion AC. Let that section be XX. Here it is marked in the diagram. Considered at a distance x from support A as shown above. So from A, the x distance is considered for the section XX because shear force is 0 in A to C. Now let us write the equation for this section only. Now shear force at XX, positive RA, that is upward 22.4 kilonewton, minus 10 into x is equal to 0. X is the distance, 10 is the UDL intensity, 0. So it is equated to 0, x is 2.24. So this distance x is 2.24. So you can see here shear force which is 0 having distance of 2.24 meter from A. Now let us go to the calculation of bending moment. Now bending moment at A, which is a simple support here, and at D, which is a free end, is 0. Bending moment at C. So 22.4, that is RA into 4. 4 is the distance that is creating a sagging bending moment, that's why positive. Minus 10 into 4, that is the load intensity into distance 4 meter into centroid of that load, that is 2 meter. 10 into 4 into 2. So bending moment at C 9.6 kilonewton meter. Bending moment at B. Now from left 22.4 into 5 meter distance minus 10 into 4 into 3 meter. So UDL is acting at the center of its portion. So distance of the centroid from B is 3 meter. Minus 2 into 1, 10 kilonewton meter negative is bending moment at B. So left side of the section is considered, or point is considered. Alternatively, MB, you can calculate moment at B from right of the section also. 5 kilonewton is a concentrated load. 5 into 2 minus 10 kilonewton meter, considering right portion of the section. Now absolute maximum bending moment is at xx, maximum bending moment. So Mmax, xx is the section where shear force is 0. So maximum bending moment is always at the point where shear force is 0. So the distance of that xx is 2.24 from A. That's why 22.4 into 2.24 minus 10 into 2.24 square by 2. This is the equation of bending moment at xx. So maximum bending moment is 25.1 kilonewton meter. Now these bending moments are coordinates are marked 9.6, 10 kilonewton negative, maximum at xx, that is 24 5.1. Now the variation of bending moment diagram, one A to C, it is UDL, so all these ordinates are joined by parabolic line. Now up to C point, so the diagram is with parabola. From C to B point, it is straight line, and from again B to D point, it is straight line. Now here in zone A to C, it is positive. From C to B, the bending moment has changed its sign from positive to negative. So this is the point where bending moment changed the sign. So this is called as point of contraflexure. Now this is our problem, example problem. This is shear force diagram. This is bending moment diagram. This point is point of contraflexure. That is where the bending moment changes the sign. Now calculation of absolute maximum bending moment. Maximum bending moment will occur at the section where shear force is 0. SFD shows that the section having 0 shear force. It is already we have solved. So maximum bending moment 25.1 kilonewton that we have solved. Now this point of contraflexure that we have to determine. Let A be the distance of point of contraflexure from support B. Here it is the support B. Now taking moments at the section AA. So just left, considering the left portion, this AA section is taken. Now MAA, that is equal to minus 5 into 2 plus A plus 24.6 into A. 24.6 is the reaction at B. So 5 is the concentrated force and it is equated to 0 because bending moment is 0 here. A is 0.51 meter from B. Thank you for your kind listening.